Suppose you're given the following question. What is the sum of the reciprocals of the roots of the equation 2003 divided by 2004x plus 1 plus 1 over x is equal to 0? Let's first try to simplify this into a form that we can probably handle much easier. So first we can convert this into a quadratic by multiplying by x. So we'll get 2003 divided by 2004, x squared plus x plus 1 equals 0. And because we're multiplying by x, and we're multiplying x by 0, nothing's going to happen to this side. And again, we'll multiply both sides by 2004 divided by 2003 to simplify things further. Equals 0. Okay. But now that we have this quadratic, what are we actually going to do with it? We're asked for the sum of the reciprocals of the roots. If the roots were r and s, we need 1 plus r plus 1, 1 divided by r plus 1 divided by s. Even if we were to use the quadratic formula in this case, which is already a cumbersome process, we still have a bunch more operations to do before we can even think of doing that. Because of that, we're going to be trying to look at this in a much faster way, using the technique known as Vieta's formulas. To understand where Vieta's formulas come from, we first have to write this polynomial in a more factored form. We have x minus r times x minus s, where r and s are the hypothetical roots of this. And that's equal to 0. And if we decide to expand this, you get x squared minus rx minus sx plus rs is equal to 0. So we're given x squared minus r plus s times x plus rs equals 0. And as you can see, there's a one-to-one correspondence between these terms here and these terms here. The coefficient of the x term, which is negative r plus s, is also equal to 2004 divided by 2003. And the product of these terms is also 2004 divided by 2003. But that still doesn't quite get us where we want, because we want 1 divided by r plus 1 divided by s. But there's a very useful and common trick in these sorts of problems that we're going to use, and that's establishing a common denominator. We're going to have r plus s divided by rs. As you can see, you can just multiply both sides here by s, both sides here by r. And clearly, we have everything we need. We have r plus s, and we have rs. Negative 2004 divided by 2003 divided by 2004 divided by 2003, which is just negative 1. And that's our answer. So already you've seen the power of Vieta's formulas, allowing us to skip a very long and cumbersome process of finding the roots and then plugging them back into the expression that we want. But Vieta's formulas are actually even more powerful than this. But let me show you what I mean. Suppose you have a general polynomial of the form x minus r sub 1 times x minus r sub 2 times x minus r sub 3. Now let's just leave it as at 3 for now, and I'll show you how it expands later. The Vieta's formulas allow us to find the coefficient of every possible power of x within this term, or within this polynomial. The coefficient of the x cubed term is 1. That I don't think I need to explain that further. The coefficient of the x squared term. So let's try to think about how we would find the coefficient of the x squared term. If you're gonna try to distribute two x's in this factored form, which is how you would make an x squared term. Let's say we're gonna use this x and this x. Then you can't distribute the next x, so you have to distribute the third root. So you're going to have negative r sub 3 x squared. And the same is true for every other x, or every other pair of x's that you can pick. You're going to have negative r2 x squared minus r1 x squared. So the coefficient of the x squared term is a negative r1 plus r2 plus r3. Okay, what about the x term? That involves you only picking one x from this entire set of three x's that we have. But that means you have to pick two of these minus r terms. So that, let's say, if you pick the first x, you have r2 times r3. And then let's say you pick another x, like this one, then you're going to have to pick r1 and r3. And by picking one x, you're forced to pick another pair of r's, of roots. So the coefficient of the x term is going to be positive 1 because there are two negatives. You're going to have minus r1 times minus r3. But it's also going to be every possible pair of these roots put together. Plus r1, r3 plus r2, r3. And for the coefficient of the x to the 0 term, or just the constant term, it's going to be minus r1 times minus r2 times minus r3, which is just the same as minus r1, r2, and r3. So these signs in Vieta's formulas are going to alternate a lot, and that'll be very important, very useful to know. And as you can see, this is not the only expansion that you can have. Let's say if you had 4 roots, the second lowest term is going to be every singleton of roots, if you will. Did I say second lowest or second highest? I'm sorry. I'll say that again, just to be clear. If you have n roots, alright, n roots, the n minus 1, the x to the n minus 1 term's coefficient is going to be every way you can pair single roots together. So it's just going to be the negative sum of all roots. Negative sum of roots. The x to the n minus 2 term is going to be the positive sum of pairs of roots. The x to the n minus 3 is going to be the negative sum of every triplet you can make. And so on, like this. Let's use this technique to solve our next question. Let r1, r2, and r3 be the roots of the polynomial x cubed minus 14x plus 15x minus 16. Compute 1 divided by r1 plus 1 by r2 plus 1 by r3. So from the previous problem, this one is actually fairly trivial already. You can decide to simplify this by establishing a common denominator, which will get you r1, r2 plus r1, r3 plus r2, r3 divided by r1, r2, and R3. Now let's go back to the polynomial that we're given. We're given x cubed plus x, crucially, there's no x squared term. Remember, the term with one power lower than the highest is the sum of the roots, which means the sum of the roots here is 0. So we have x cubed plus x minus 16. Okay. So from here, these two terms look fairly familiar. This is the product of all the roots. This is the sum of all the pairs. And here, we can already pretty easily find the product of all the roots and the sum of the pairs. We're given that the sum of the pairs, the coefficient of x. Oh, actually, you have to be careful about the signs. So let's just go over this again. We have x cubed minus 0x squared, right? Plus 1x minus 16, right? So that's how it should be. Let's say in the previous expression that we had here, the signs did in fact alternate starting from positive. And here, they also do that. If it ever breaks that pattern, you'd simply take the negative. So, for example, this was a negative x, then the sum of the pairs wouldn't be 1, but negative 1. But in this case, it's 1, and the denominator is 16. So your answer is 1/16. Okay, good. Who's this? Our next question is going to be using a different technique. As you will see, you'll definitely need it. All the roots of the polynomial z to the 6th minus 10z to the 5th plus az to the 4th plus bz cubed plus cz squared plus dz plus 16 are positive integers, possibly repeated. What is the value of b? So already, this is an incredibly hard question. We're given very little information. We're given the sum of the roots, that the leading term is 1, the leading coefficient is 1, and that the product, so minus, plus, minus, plus, minus, plus, is 16. The product of the roots is 16. So, in order to figure out how we might find these roots, it's important to realize that every single one has been defined to be a positive integer. That's very, very important. And we're also allowed to repeat them. That's going to be a bit important later. Let's say we rewrite this polynomial again with hypothetical roots. X minus, oh my god, minus r times x minus s times x minus t. Let's leave it there. I don't want to make this bigger than it has to be. You're going to have, how do I get rid of this? I don't know, it doesn't matter. You have x cubed, a bunch of things in between that actually aren't relevant for our theorem, times minus r s t. And what's interesting to note here is that the factors of this constant term could potentially be a root of the polynomial, because we're given that every root is a positive integer, or rational at least, and what that implies is that they have to be a factor of the constant. Now let's say we multiply. There was a leading term that wasn't just 1, so we have ax cubed, and that would go to every term in the polynomial, including the constant term. So now you have to divide out by a factor of a if you want the roots. So basically, this theorem is called the rational root theorem, and what it says is that any root of this polynomial can be expressed as a factor of the constant term divided by factor of the leading coefficient. So let's use that here to our advantage. Here we're given that all the roots are positive integers and that the leading coefficient is 1, so we don't need to worry about that. And we're given that they're all positive, so we don't have to worry about positive factors of 16. And those are 1, 2, 4, 8, and 16. Yeah. Now we're asked to find the value of b. Well, first we have to find a way to make these roots in such a way that their product is going to be 16 and their sum is going to be equal to 10. Okay. So we might think that with a lot of roots and a very relatively small sum, we should probably try to maximize the number of small terms we have, like 1 and 2. But we also have to figure out how to make a 16 out of this. We obviously can't use 16 because that would already be too big. If we use 8, we would have 8, and then what? Even if we put 1s for the other 5 terms, that's already too big. So that doesn't work either. We can't use 8. Perhaps if we tried 4, which would require us to use 4 times 4, we still have 4 more spots, and we have to fill those all with 1s, which will lead us to a sum of 12. Not what we want either. So we can only use 1s and 2s. So if we want to make 16 with only 2s, you need 4 2s and conveniently 2 extra spots left for just 1s. Okay. And now you're asked a much more difficult question. You found the roots. Now what's the value of b? So b, if you remember, positive, negative, okay. So whatever we get at the end, we have to negate. And b, if you remember, was actually, wait, yeah, b, if you remember, was the sum of every triple of roots. So b is gonna be either something like that, or every term in b is gonna be something like 2 times 2 times 2, or 2 times 2 times 1, 2 times 1 times 1, and you'll notice, actually, it can't be anything else. These are the only 3 options that you can have, which is really convenient, because let's say these were really various, like you had 1, 2, 3, 4, and 5, it would be an absolute nightmare to have to calculate b. But fortunately, there are only 3 cases, so if we can count how many times each of these happens, it should be relatively easy to find the value of b. But let's first try to find out how many times this case happens. So you're already multiplying by all of the 1s, and you just have 4 2s that you can select from for the last 2. So that's just going to be 4. Yeah, the order in which you put the terms doesn't matter. So let's say you had x minus 2 times x minus 2 times x minus 1. It's the same as if you get minus 4x. If you get minus 4x like that, or if you get it like that, if that makes any sense. the order basically doesn't matter. You're just choosing the numbers which to multiply. Okay, so the next possibility you're given is that, or let's actually move on to the easiest one. The next possibility you're given is that everything is all twos. Okay, so that's just how many ways are there to choose three from the four twos you're given. 4 2 3, which is just 4. Okay, now the hard part, obviously, you have 2 times 2 times 1. You have two choices of 1. You can pick this one or this one. Uh, okay, let's label. These roots are distinguishable, obviously, because while they're the same value, it's gonna matter. You're gonna have multiple of these, right? I hope that's obvious. You can choose either E or F to be the one you want. So you have two choices of 1, and you also have a bunch of choices for which pair of 2 you're gonna pick. So which pair of 2 you're gonna pick out of 4? That's 4 choose 2, which is 4 times 3 divided by 2 times 1. That's 6. That's 12. You're gonna have 4, 12, and 4. That is actually no. You can't do that yet. I'm sorry. You have 4 times 8 as your value there. You have 12 times 4, and here you have 4 times 2. So that's 48 plus 32 plus 8, 88. And remember, it had to be negative. Yeah, it had to be negative, so you're gonna get negative 88 as your answer. So, while you can definitely use theorems to like trivialize problems almost to your advantage, sometimes you also have to do a lot of thinking to solve these. Like in this question, 2008, Amy 2, number 7. Let R, S, and T be the three roots of the following equation: 8x cubed plus 1001x plus 2008 equal to 0. Find R plus S cubed plus S plus T cubed plus T plus R cubed. Okay. So first that looks rather daunting, but you can realize that R plus S is the sum of the roots but missing a term. So you have the sum of the roots minus T. It's just kind of confusing. Let's just add like a V for sum. I don't know. It's just the first thing that came to mind. You have a V minus R, and you have a V minus S cubed. But what you'll notice is that there's no x squared term here. That means V is 0, which is very convenient for us. You have minus T cubed, minus R cubed, minus S cubed. Okay. All right. Let's look at it here. So minus R cubed minus T cubed minus S cubed. So now, this still is not an easy task to find, right? You've cubed everything, but you haven't actually like cubed the sum itself. You haven't cubed R plus S plus T. But actually, that might be a really good idea to do, right? Like if you have R plus S plus T and you cube the whole expression, you will definitely be able to find R cubed plus T cubed plus S cubed and some extras that you can hopefully define conveniently in terms of these coefficients that you already have. Right. And here I should mention that 1001 is not itself something, a function of the roots. That would actually be 1001 divided by 8. And same here, 2008 divided by 8. That's important because there's actually a leading coefficient. So if you want the product of all the roots, it's going to be actually negative 2008. And that's the product of all the roots. And this is the sum of all the pairs of the roots. That's going to be probably important later on. So here we have r plus s plus t times r plus s plus t. From here, you can easily find r cubed like so, s cubed, and t cubed in the same fashion. But let's see what other terms you can find. If you have r squared in general, like that, you can find r squared times s plus r squared times t. And you also have a couple selections of which r you're going to pick. So you can pick that r, or that pair of r, or that pair of r. 3 pairs of r you can pick. So it's going to be 3 of those. But as you'll notice, it doesn't actually matter if that you pick 2 r's. It's also the same story for 2 s's. You'll have s squared t plus s squared r, and then t squared r plus t squared s. Notice this also takes care of all the cases where you only wanted to pick one of them, except for that last possibility where you wanted to pick r, s, and t separately. So you have r, s, t like that. How many of those will you have? Well, you have 3 choices of r. You can pick that r, or that r. But then once you pick an r, like from here, you can't pick the s from there, right? So you have to pick an s from there or there. So you have 2 choices of s, and then in the same way you only have 1 choice of t. So it's going to be plus 6rst. Alright? But now, what do we do from here? Because r squared s plus r squared t, that doesn't seem very convenient to try and find, does it? Let's try and expand this out so we can maybe see a pattern easier. S cubed plus t cubed. Well, maybe from here, if we, for example, take out the rs, you can get an r plus an s, and, well, you won't get a t, but you can get a t from there, actually. So you can have r plus s plus t, and you can have 3 of those, and you will also have rst's over there left over. But you know what, actually it might be more prudent to leave the t behind as its own term. So we have 3 times rs times, or 3 rs times r plus s plus 3 r t times r plus t plus 3 ts times t plus s. Okay, we can rewrite this again as 3r s times negative t plus 3rt times negative s plus 3ts times negative r. Remember, because the sum of the roots is 0. So this actually is very useful, because now we've just simplify this whole expression in terms of RST or in terms of R cubed, S cubed, and T cubed as we wanted. Oh, and you might want to remember this, what this actually was. This was the sum of all the roots cubed, which is just equal to 0. So this is very useful. We have automatically minus 9 RST plus 6 RST there, which means that you'll end up with R cubed plus S cubed plus T cubed minus 3RST is going to be equal to 0, which means that R cubed plus S cubed plus T cubed is equal to 3RST. And what we wanted is the negative of that. So we're going to say negative R cubed minus S cubed minus T cubed equals minus 3RST. And RST, if you remember, was negative 2008 divided by 8. So let's just quickly do the long division for that. So you have 251 as 2008 divided by 8. So your answer should be negative 753. Alright. And now for our last question. Let Sk denote the sum of the kth powers of the roots of the polynomial x cubed minus 5x squared plus 8x minus 13. In particular, S0 equals 3, S1 equals 5, and S2 equals 9. Let A, B, C be real numbers such that Sk plus 1 equals A, Sk plus B, Sk plus 1 equals Ask plus Bsk minus 1 plus Csk minus 2 for k going from 2, 3, and on and on and on. Alright, and we want what is A plus B plus C. So this idea of the sum of the kth powers of the roots of the polynomial of a polynomial is actually a very well-known idea, and to find it we use a technique known as Newton's sums. And we kind of use that here, right? Because R plus S plus T, each term cubed, is its sort of kth power, or the sum of the kth power of the roots. But this technique is much more generalizable. So we're already given that R to the 0 plus S to the 0 plus T to the 0 equals 3. This is obvious. You're given S sub 1 is equal to 5. R plus S plus T is equal to 5. And now you're given R squared plus S squared plus T squared is equal to 9. Okay. Let's say you weren't given that. How would you find R squared plus S squared plus T squared? Well, we can try what we did last time. We have R plus S plus T, which we can square. And you have R squared plus S squared plus T squared plus, but let me just write this out for convenience so that's easy for you to see. Once you've picked every repetition, you're going to pick all the terms that aren't squares. So that's RS RT, but you can also go the other way. You can have RS and RT, so it's going to be 2 times every pair. So that's RS plus RT plus ST. And actually, we know how to find RS plus RT plus ST. RS plus RT plus ST is that right here. That's 8. And you're going to have 8 times 2 plus R squared plus S squared plus T squared is equal to R plus S plus T squared, which is 25. Alright, maybe we can write this in terms of the coefficients a bit more abstractly. So, we already know that this is S sub 2, and we have 2 times, well, what is this exactly? You have the leading coefficient, which we'll say is a to the n, or a sub n. You have a sub n minus 1 times a sub n minus 2. So you have plus 2 times a sub n minus 2 divided by a sub n, which is equal to a sub n minus 1 divided by a sub n, the whole squared, which means that we were going to have something that looks like this, except you don't actually have to define it as a sub n to the n minus 1 squared. You can also define it as this. So let's take out the squared from here as well. We're going to have a times, or a sub n minus 1 times, what's another way to write the sum of all the roots? It's just s sub 1. And you don't need to divide by a sub n for that. So the expression you're going to end up with is a n s2. Oh yeah, and the this coefficient you have to make negative, because as you remember from Vieta's formulas, this is negative by default, and if you want the sum of the roots, you have to make it positive. So you're going to have a sub n times s2 plus a sub n minus 1 times s1 plus a sub n minus 2 times 2 equals 0. And this is actually a general formula that you can use for any kth power that you might want, or any sum of squares that you might want. But this can also apply to cubics, or any third powers. So it'll look something like this. Plus 3 times a to the n minus 3 equals 0. And if, let's say, this term is not present because it's just a quadratic, you'd omit it from the expansion. Okay, let's see if we can use this to help us. So we're already given that this is 9. Let ABC be real numbers such that sk plus 1 equals a. Okay, so let's write this in terms of a Newton sum. We have 0, or sk plus 1 minus A sk plus B sk bsk minus 1 plus csk minus 2, and that's all equal to 0. And once again, I'm forgetting the signs. Yeah. So this is the expression that we're given. And for k is equal to 2 and 3 and so on. Okay. For 2, let's say k is 2, given as 2 minus a, sorry, k is 2, not k plus 1. That's 3 minus a as 2 minus b as 1 minus c as 0 equals 0. Well, because there's no s0, this is just going to be minus 2c. Alright, so here, this is almost a Newton sum expression, right? Like the one we had here. We just need to change a couple of the terms. So first of all, clearly, every single one of these terms is being divided by an minus 1. Sorry, an. Well, actually, it might be more convenient to make all of these CS, CS1, 2, 3, 4, right? Like that. So clearly all of these are being divided by a sub n, and they're all on the wrong sign, right? So we have here, a should be negative if we go back. That should be a sub n minus 1, which is just the next coefficient. So that is a to the negative 5, and this should be negative of whatever the next coefficient is, which is 8. And you'll notice actually we don't need to keep bothering about writing an, because an is actually just 1 here. There's no a sub n. So that's quite convenient. And here, for minus cs, you should have negative of negative 13. And what we wanted was the sum of all of this. We have 5 minus 8 plus 13, which is just 10. And that's our answer. So with all of these techniques, I challenge you to solve these two problems. You might want to think a little bit more out of the box for some of these, but they're only two problems. I think you'll be fine. So have fun. Bye.